You know, when you're monitoring machinery, one single choice can mean the difference between everything running smoothly and a complete, costly disaster. And that choice? It's often between an accelerometer and a velocity sensor. Today, we're going to break down exactly how to pick the right tool for the job.
Just imagine this for a second. A critical piece of machinery in your plant just stops. Production grinds to a halt. And every minute that thing is down, you're just bleeding money. It's an absolute nightmare scenario, right? And it could all have started from one tiny mistake, picking the wrong sensor to listen in on its health. But hey, that's exactly why we're here. In this explainer, we are going to walk through a really clear, step-by-step process so you can make the right call every single time. No more guesswork.
Okay, so first things first. Let's meet our two main characters, our vibration detectives, if you will. Now, on the surface, they both measure vibration, but, and this is a big but, they do it in fundamentally different ways. Understanding this is step number one.
So you've got the accelerometer, and you guessed it, it measures acceleration. That's the rate of change in motion. Think about when you slam on the gas in your car and you get pushed back in your seat. That's acceleration. It's fantastic at picking up on those sudden impacts and really high-frequency jitters.
Then you have the velocity sensor. This one measures velocity, or just plain speed. It's less like flooring the gas and more like looking at your car's speedometer. It's measuring the steady speed of the vibration, not that sudden change in speed.
All right, let's get practical. The very first question you have to ask yourself is a big one. Seriously, it's probably the most important, and it will immediately cut your options in half. Are you looking inside the machine or at its surface?
So are you interested in what's happening deep inside the machine, the actual movement of the shaft? Or are you more focused on the vibrations you can feel on the outside, on the machine's casing? Now, for shaft motion, you'd probably use something else, like a proximity probe. But for that external casing motion, well, that's where we have the big showdown between our two detectives.
So if you've decided you're measuring the casing, here's some general rules of thumb. You'll typically use these sensors on machines with rolling element bearings, your common ball bearings, or on big, stiff reciprocating machines like compressors. But what's really important here are those last 3 points. The choice really boils down to signal strength. A weak signal just gets lost in all the background electronic noise, which makes your sensor pretty much useless. And that right there, that's a huge clue. Speed matters a lot.
Okay, so now that we know where we're going to measure, we need to figure out what we're trying to listen for. Think of it like a doctor diagnosing a problem. Different issues inside the machine, like unbalance or a bad bearing, create vibrations at very specific frequencies.
And this is absolutely crucial. You have to know what you're listening for. Every potential problem, every fault, kind of sings at its own unique pitch or frequency. If you pick a sensor that's basically deaf to that frequency, it's like trying to hear someone whisper during a rock concert. It's not going to work.
All right, let's make this real. Check out this example of a pump running at 3,000 RPM. We can actually calculate the frequencies for different potential problems. See? Rotor issues are down in the low range, blade problems are in the middle, and bearing defects can shoot all the way up to 1,500 Hertz. So whatever sensor we pick, it needs to be really effective across that entire range, from as low as 12.5 all the way up to 1,500 Hertz.
And that brings us to the main event. We know the frequency range we need to cover. Now we have to find a sensor that can give us a strong, clear electrical signal in that range. And this is where accelerometers and velocity sensors really show their true colors.
This quote from the source material really just nails it. Think of it this way. When things are moving really fast, you get a lot of jarring acceleration. When things are moving slowly, you get these big, slow movements. That's displacement. But velocity, it's kind of the happy medium. It stays much more consistent no matter the speed. Okay, so let's actually put some numbers on the board. This table shows the electrical signal strength in millivolts for the same amount of vibration, but at 3 different speeds. Now look closely. See how the velocity sensor's signal is just locked in at 50 millivolts? Meanwhile, the other two are all over the place. Now let's visualize this, because this is where it gets really clear. At a low speed of 600 RPM, just look at that sad little bar for the accelerometer. It's only 8 millivolts. That signal is so weak it could easily just get swallowed up by background noise. The velocity sensor, though, it's giving a nice solid 50 millivolt signal. It is the clear winner here, no contest.
Okay, now let's go to that medium speed, like our pump from the example, 3,000 RPM. And now things get pretty interesting. The accelerometer's signal has jumped up to a respectable 41 millivolts, which is really close to the velocity sensor's 50. So at this speed, you could really go either way. Both are giving you a strong, usable signal. But
Watch what happens when we really crank up the speed to 30,000 RPM. The tables have completely turned. Look at the accelerometer signal now. It's a massive 405 millivolts. This just perfectly shows its strength. For high-speed stuff, the accelerometer is the undisputed champion. It gives you the strongest clear signal by a mile.
So what's the big takeaway from all this? What's the secret sauce?
It is all about the matchup. You have to line up the sensor that performs best, the one that gives you the strongest signal, with your machine's operating speed and the specific problems you're trying to find. Low speeds love velocity sensors. High speeds are an accelerometer's game.
We've looked at the machine, we've decoded the frequencies, and we have just witnessed the signal strength showdown. So now, it's time to bring it all home and make our final, confident decision.
Okay, before you go and click Buy Now, there are just a few last real-world things to think about. Is it going to get super hot where this sensor is going? Is there a chance it could get wet or even submerged? Does it need to be approved for a hazardous environment? These are the practical questions that can be the final tiebreaker.
So, to wrap it all up with a neat little bow, velocity sensors are amazing all-rounders, especially for those common medium-speed machines running with ball or roller bearings. They're also going to be your best bet for just general overall vibration on slower reciprocating machines. Accelerometers? They're your go-to for anything high speed. And they're also great for catching those sharp, high-frequency impacts, like a valve slamming shut. So there you have it. You now have the framework to pick the right tool for the job. You know how to decode the signals, how to pick the sensor that can hear exactly what you need it to. So the only real question left is, now that you actually know how to listen, what is your machinery trying to tell you?